So for this sample problem, we're looking at a pilot flying a small plane at 56.6 meters per second in a circular path with a radius of 188.5 meters. And sorry about the noise. We got a trash can through the hallway. The centripetal force needed to maintain the plane's circular motion is 1.89 times 10 to the fourth newtons, and we want to find the mass of the plane. So again, we've got a plane flying in a circular path, and I cannot draw circles to save my life. Okay, here's the center of its path, or where the axis of rotation would be. Okay, it says that, let's draw, here's our little plane. Okay, all objects are circles. It says that it's got a tangential speed, we know VT, of 56.6 meters per second. Okay. And the radius, so R, so I'm going to write R out here. Radius is 188.5 meters. The centripetal force, so the force that is directed towards the center, that helps pull the plane in and maintain its circular motion, is 1.89 times 10 to the fourth newtons. Okay, and we want to find the mass of the plane. All right, well, we know that the centripetal force is equal to mass times centripetal acceleration. This is just another application of Newton's second law. But we also know that centripetal acceleration is equal to our tangential speed squared divided by the radius. So we can rewrite this whole thing as centripetal force is equal to mass times Vt squared over r. Okay, we want to isolate mass, so we're just going to divide by the reciprocal, or multiply by the reciprocal, or divide by this same exact fraction here for Vt squared over r. So I'm just going to multiply by the reciprocal to do the same thing. I have to do that on both sides. Okay, so now all that stuff cancels. We can rewrite this as, I'm going to write it down here, as mass now is equal to our centripetal force times r over my tangential speed squared. Okay, go ahead and plug in what we know. So we've got 1.89 times 10 to the fourth newtons, okay, times the radius, so 188.5 meters, all divided by 56.6 meters per second, and this whole chunk is squared. Okay. If I look at my numerator, remember newtons here is a kilogram meter per second squared. Okay, so kilogram meter per second squared, mass times acceleration. All right, and then we've got times in meters. So we should see that our meters will end up squaring up top. So our numerator now should have kilogram meters squared per second squared, and that is a joule. But instead of recognizing that and making it a joule, we're going to keep it like this, so that way we can see how units cancel at the bottom. Okay, so I'm going to take those two numbers and go ahead and multiply that out to solve for my numerator. Remember, when I've got a number in scientific notation, let's put it in parentheses. Can you see that? Yeah, you can, kind of. Let's see if you get less of a glare right here. Okay, so we're going to put that in parentheses and then use the E button right here, right there, to show that exponent. So I've got 1.89. That E is read as times 10 to the fourth. For that number, times 188.5. So I'm going to write this in scientific notation as 3.51 times 10 to the 36. Okay, all divided by 56.6 squared is 3.20 times 10 to the third. And now I've got meter squared per second squared, because remember, this square, since it's on the outside, goes to everything inside of the parentheses. Okay. I see if I'm dividing these two terms, my meter squared and second squared, will cancel, and I'm left with just kilograms, which is perfect for mass. Okay, now I'm going to take my numerator and divide it by my denominator. Since that's in scientific notation, 3.51 times 10 to the 6th divided by 3.20 times 10 to the 3rd. Okay. And we get 1.10 times 10 to the 3rd kilograms. Okay. Another way you could write this would be 1,100 kilograms. All right.